Hi there, I welcome you all in this learning video. Till now we have taken a distribution, probability distribution, namely a binomial or Bernoulli distribution. Now here in this learning video we are going to talk about the Poisson distribution. So let me tell you about the Poisson distribution. Poisson distribution has varied applications in many of the fields. So it is used to determine the maximum and minimum number of times the event will occur within the specified time. Okay, so time is a factor over here. Then the second thing is this Poisson distribution. So companies can utilize this Poisson distribution to examine how they may be able to take the steps in order to improve the operational efficiency. For instance, an analysis done with the Poisson distribution might reveal how a company can arrange the staffing in order to be able to better handle the peak periods of the customer service calls. Okay, so these are the things that one can look for with the help of Poisson distribution. Okay, so let us see what is Poisson distribution. It is defined for the discrete random variable. So let x be a discrete random variable having the probability function this f of x is equal to e to the power minus lambda into lambda to the power x upon x factorial, where x varying from 0, 1, 2 and so on, where lambda is a positive constant. The next thing is the distribution is called Poisson distribution, and a random variable x having this distribution is called as Poisson distributed. Okay, now there is a relation between binomial and the Poisson distribution, and later on we'll see the establishment of the validity of Poisson's approximation to binomial approximation. Okay, so if the number of trials is greater than equal to 50 in the binomial distribution, which is large, and the probability of success is close to 0, such that NP is constant, then the binomial distribution is closely approximated to a Poisson distribution. This Poisson distribution involves only one parameter, whereas in the case of binomial distribution we have the two parameters, namely the trials, number of trials, and the probability of success. Okay, so this is about the Poisson distribution. Now I would like to take a result or the result on the establishment of the validity of Poisson's approximation to binomial distribution. Okay, so let me write down that establishment as a theorem. So I'm writing this as a theorem. So it is like the limiting form of binomial, distribution as n tends to infinity, binomial distribution as n tends to infinity and p tends to 0, it is like probability of success is approaching towards 0, is such that np is equal to lambda, is such that np is equal to lambda, where lambda is a fixed positive constant or a number, is Poisson distribution, is Poisson distribution. Sometimes this can also be asked like establish establish the validity, sorry, or it can also be as like establish the validity, establish the validity of Poisson's approximation, of Poisson's approximation, Poisson's approximation to binomial distribution, to binomial or Bernoulli's distribution. Okay, so we are given that the random variable x is binomially distributed, and we have to establish the validity of Poisson's approximation to binomial distribution. Okay, so what we are going to start with, we are going to start with the binomial distribution, and we should arrive at a Poisson distribution with the help of this given thing. Okay, so you can write here, we know that if x is binomially distributed, then what is my probability function? Then probability of x is equal to x is nothing but NCX p to the power NCX p to the power x into q to the power n minus x. Okay, just give me a moment. Yes, that is the case where we can write one thing, that is where expectation of x, or you call it as mu, is equal to np, that we have already seen in the property of binomial distribution. Okay, now we are given that lambda is equal to np, this is given, lambda is equal to np. So what is p? This implies p is equal to lambda by n. Simple. Also if p is lambda by n, then q is what? Q is 1 minus p, so that is 1 minus lambda by n. Simple. Say this is to be equation 1. Now what I am going to do is to this is the binomial distribution. Now we have to approx the Poisson. So what you have to do is you just substitute all these values over here. So you can write it as the probability of x is equal to x is equal to NCX. Okay, so what I should write here? NCX, then n choose x, then p is lambda by n power x into what is q? Q is my 1 minus lambda by n power n minus x. Simple. Now what I have used equation 1 to write down this. Simple. Now this NCX can be written as n into n minus 1 into n minus 2, likewise n into n minus x minus 1, yeah, x minus 1, okay, upon factorial x into, now this can be written as lambda to the power x upon lambda to the power x upon n to the power x, and I will write this as 1 minus lambda by n power n minus x. Okay. Now in the next step, what you can do is you can just take out n common from each of the term. So this is like probability of x is equal to x. Now what you can do is you can take out common n from each term. We have already n you can find out n from here. So you can write n into, if I take n outside, so it become n square. Now take out n common from here, take out n common from here. So it is n into n into n, how many times? X times. And what is remaining? Remaining is 1 minus 1 by n. Then it is 2 minus 1 by n, and so on, upon what is the last term? It would be 1 minus x minus 1 by n. Okay, upon this is factorial x, and we have lambda power x upon n to the power x, into, you can just separate this 1 minus lambda upon n as 1 minus lambda by n. I will try to solve it separately. Okay, so this get cancelled with this. Now I am gonna take this value separately, that is 1 minus lambda by n. I am taking these values like letting, because condition is given, letting n tends to infinity, then 1 minus 1 by n to, sorry, this would be 1, n minus 2, that would be 2 by n, yeah, yes, okay. So this is 1 minus 2 by n, and so on, then 1 minus of x minus 1 by n. All these terms contribute to 1, because 1 by n, 1 by infinity tends to 0, likewise this 2 by infinity tends to 0 as n tends to infinity, so this all tends to 1. Okay, while when you take limit as n tends to infinity to this, 1 minus lambda power n minus x, which can be written as 1 minus lambda by n power n into 1 minus lambda by n power minus x. Is it? Okay. So when you take limit as n tends to infinity, this particular term will contribute to e power minus lambda, and this contribute to some number divided by n as n tends to infinity. So this will tending towards 0. So this tending towards 0 means 1 minus 0, that is 1. Okay, why this is comes out to be e to the power minus lambda? It is like 1 minus 1 by n power n is e to the power, if it is plus then it is e to the power 1, because it is minus and here it is lambda, so this is minus lambda. Okay, so that is the result, limit as n tends to infinity. So we got this to be e to the power minus lambda. Okay, so what we remain with then, it follows that as n tends to infinity, lambda keeping fixed, that is p tends to 0, therefore probability of x is equal to x, because all this term tending to 1, okay, this is tending to e to the power minus lambda. So what we remain with when you let lambda n tends to 0 and p tends to 0, n tends to infinity and p tends to 0, so it is like lambda power x upon x factorial into 1 minus lambda by n, this is nothing but e to the power minus lambda, okay, which is nothing but a Poisson distribution, distribution. Okay, so we have just seen how a binomial distribution can be approximated to Poisson distribution, or we have seen, in other words, the validity of Poisson approximation to binomial distribution. Okay, so this is what we have in this learning video. I hope this is clear to you, because uh, mechanical steps are there, and if you have any doubt you can contact me. And thank you for watching, and have a good day.